Metallic bonding occurs as a result of electromagnetism and describes the electrostatic attractive force that occurs between conduction electrons and positively charged metal ions. It may be described as the sharing of free electrons among the lattice of positively charged ions. In a more quantum mechanical view, the conduction electrons divide their density equally over all atoms that function as neutral entities. Metallic bonding accounts for many physical properties of metals, such as strength, ductility, thermal and electrical resistivity and conductivity, opacity, and luster. Metallic bonding is not the only type of chemical bonding a metal can exhibit, even as a pure substance. For example, elemental gallium consists of covalently bound pairs of atoms in both liquid and solid state. These pairs form a crystal lattice with metallic bonding between them. Another example of a metal-metal covalent bond is mercurous ion. History. As chemistry developed into a science, it became clear that metals formed the large majority of the periodic table of the elements, and great progress was made in the description of the salts that can be formed in reactions with acids. With the advent of electrochemistry, it became clear that metals generally go into solution as positively charged ions in the oxidation reactions of the metals became well understood in the electrochemical theories. A picture emerged of metals as positive ions held together by an ocean of negative electrons. With the advent of quantum mechanics, this picture was given more formal interpretation in the form of the free electron model and its further extension, the nearly free electron model. In both of these models, the electrons are seen as a gas traveling through the lattice of the solid with an energy that is essentially isotropic in that it depends on the square of the magnitude, not the direction of the momentum vector k. In three-dimensional k-space, the center points of the highest filled levels should therefore be a sphere. In the nearly free correction of the model, box-like Brillouin zones are added to k-space by the periodic potential experienced from the lattice, thus mildly breaking the isotropy. The advent of X-ray diffraction and thermal analysis made it possible to study the structure of crystalline solids, including metals and their alloys, and the construction of phase diagrams became accessible. Despite all this progress, the nature of intermetallic compounds and alloys largely remained a mystery, and their study was often empirical. Chemists generally steered away from anything that did not seem to follow Dalton's laws of multiple proportions, and the problem was considered the domain of a different science, metallurgy. The almost free electron model was eagerly taken up by some researchers in this field, notably Hume Rothery, in an attempt to explain why certain intermetallic alloys with certain compositions would form and others would not. Initially, his attempts were quite successful. His idea was to add electrons to inflate the spherical Fermi balloon inside the series of Brillouin boxes and determine when a certain box would be full. This indeed predicted a fairly large number of observed alloy compositions. Unfortunately, as soon as cyclotron resonance became available and the shape of the balloon could be determined, it was found that the assumption that the balloon was spherical did not hold at all, except perhaps in the case of cesium. This reduced many of the conclusions to examples of how a model can sometimes give a whole series of correct predictions, yet still be wrong. The free electron debacle showed researchers that the model assuming that the ions were in a sea of free electrons needed modification, and so a number of quantum mechanical models such as band structure calculations based on molecular orbitals or the density functional theory were developed. The free electron picture has, nevertheless, remained a dominant one in education. The electronic band structure model became a major focus not only for the study of metals but even more so for the study of semiconductors. Together with the electronic states, the vibrational states were also shown to form bands. Rudolf Peierls showed that, in the case of a one-dimensional row of metallic atoms, say hydrogen, an instability had to arise that would lead to the breakup of such a chain into individual molecules. This sparked an interest in the general question, when is collective metallic bonding stable and when will a more localized form of bonding take its place? Much research went into the study of clustering of metal atoms. As powerful as the concept of the band structure proved to be in the description of metallic bonding, it does have a drawback. It remains a one-electron approximation to a multitudinous many-body problem. In other words, the energy states of each electron are described as if all the other electrons simply form a homogeneous background. Researchers like Mott and Hubbard realized that this was perhaps appropriate for strongly delocalized S and P electrons, but for D electrons, and even more for F electrons, the interaction with electrons in the local environment may become stronger than the delocalization that leads to broad bands. Thus, the transition from localized unpaired electrons to itinerant ones partaking in metallic bonding became more comprehensible. The nature of metallic bonding. The combination of two phenomena gives rise to metallic bonding: delocalization of electrons and the availability of a far larger number of delocalized energy states than of delocalized electrons. The latter could be called electron deficiency. In 2D, graphene is an example of two-dimensional metallic bonding. Its metallic bonds are similar to aromatic bonding in benzene, naphthalene, anthracene, overlene, and so on. A one-atom thick layer of hexagonal boron nitride (Bn) is obtained, that is isoelectronic to graphene. This material, where boron and nitrogen atoms alternate, is a semiconductor, exemplifying that delocalization is a necessary but not sufficient requirement for conductivity. Electrical conductivity does occur in graphene, because the pi and pi *like bands overlap, making it a semi-metal, with partly filled bands, fulfilling the other requirement for conductivity. In 3D, metal aromaticity in metal clusters is another example of delocalization, this time often in three-dimensional entities. Metals take the delocalization principle to its extreme, and one could say that a crystal of a metal represents a single molecule over which all conduction electrons are delocalized in all three dimensions. This means that inside the metal one can generally not distinguish molecules, so that the metallic bonding is neither intra nor intermolecular. Non-molecular would perhaps be a better term. Metallic bonding is mostly nonpolar, because even in alloys there is little difference among the electronegativities of the atoms participating in the bonding interaction. Thus, metallic bonding is an extremely delocalized communal form of covalent bonding. In a sense, metallic bonding is not a new type of bonding at all, therefore, and it describes the bonding only as present in a chunk of condensed matter, be it crystalline, solid, liquid, or even glass. Metallic vapors, by contrast, are often atomic, or at times contain molecules like Na2 held together by a more conventional covalent bond. This is why it is not correct to speak of a single metallic bond. The delocalization is most pronounced for S and P electrons. For cesium it is so strong that the electrons are virtually free from the cesium atoms to form a gas constrained only by the surface of the metal. For cesium, therefore, the picture of Cs+ ions held together by a negatively charged electron gas is not too inaccurate. For other elements the electrons are less free, in that they still experience the potential of the metal atoms, sometimes quite strongly. They require a more intricate quantum mechanical treatment in which the atoms are viewed as neutral, much like the carbon atoms in benzene. For D and especially F electrons the delocalization is not strong at all, and this explains why these electrons are able to continue behaving as unpaired electrons that retain their spin, adding interesting magnetic properties to these metals. Electron deficiency and mobility. Metal atoms contain few electrons in their valence shells relative to their periods or energy levels. They are electron-deficient elements, and the communal sharing does not change that. There remain far more available energy states than there are shared electrons. Both requirements for conductivity are therefore fulfilled. Strong delocalization and partly filled energy bands. Such electrons can therefore easily change from one energy state into a slightly different one. Thus, not only do they become delocalized, forming a sea of electrons permeating the lattice, but they are also able to migrate through the lattice when an external electrical field is imposed, leading to electrical conductivity. Without the field, there are electrons moving equally in all directions. Under the field, some will adjust their state slightly, adopting a different wave vector. As a consequence, there will be more moving one way than the other and a net current will result. The freedom of conduction electrons to migrate also give metal atoms, or layers of them, the capacity to slide past each other. Locally, bonds can easily be broken and replaced by new ones after the deformation. This process does not affect the communal metallic bonding very much. This gives rise to metals' typical characteristic phenomena of malleability and ductility. This is particularly true for pure elements. Gold, for example, is very soft in pure form, which is why alloys of 18 karat or lower are preferred in jewelry. Metals are typically also good conductors of heat, but the conduction electrons only contribute partly to this phenomenon. Collective vibrations of the atoms known as phonons that travel through the solid as a wave contribute strongly. However, the latter also holds for a substance like diamond. It conducts heat quite well but not electricity. The latter is not a consequence of the fact that delocalization is absent in diamond, but simply that carbon is not electron deficient. The electron deficiency is an important point in distinguishing metallic from more conventional covalent bonding. Thus, we should amend the expression given above into: metallic bonding is an extremely delocalized communal form of electron-deficient covalent bonding. Metallic radius. Metallic radius is defined as 1/2 of the distance between the two adjacent metal ions in the metallic lattice. This radius depends on the nature of the atom as well as its environment, specifically, on the coordination number, which in turn depends on the temperature and applied pressure. When comparing periodic trends in the size of atoms, it is often desirable to apply so-called Goldschmidt correction, which converts the radii to the values the atoms would have if they were 12 coordinated. Since metallic radii are always biggest for the highest coordination number, correction for less dense coordinations involves multiplying by x, where 0 less than x less than 1. Specifically, for Cn equals 4, x equals 0.88, for Cn equals 6, x equals 0.96, and for Cn equals 8, x equals 0.97. The correction is named after Victor Goldschmidt, who obtained the numerical values quoted above. The radii follow general periodic trends. They decrease across the period due to increase in the effective nuclear charge, which is not offset by the increased number of valence electrons. The radii also increase down the group due to increase in principal quantum number. Between rows 3 and 4, the lanthanide contraction is observed. There is very little increase of the radius down the group due to the presence of Pauli shielding f orbitals. Strength of the bond. The atoms in metals have a strong attractive force between them. Much energy is required to overcome it. Therefore, metals often have high boiling points, with tungsten being extremely high. A remarkable exception are the elements of the zinc group, zinc, Cd, and Hg. Their electron configuration ends in Ns2, and this comes to resemble a noble gas configuration like that of helium more and more when going down in the periodic table because the energy distance to the empty np orbitals becomes larger. These metals are therefore relatively volatile, and are avoided in ultra-high vacuum systems. Otherwise, metallic bonding can be very strong, even in molten metals, such as gallium. Even though gallium will melt from the heat of one's hand just above room temperature, its boiling point is not far from that of copper. Molten gallium is therefore a very non-volatile liquid thanks to its strong metallic bonding. The strong bonding of metals in the liquid form demonstrates that the energy of a metallic bond is not a strong function of the direction of the metallic bond. This lack of bond directionality is a direct consequence of electron delocalization, and is best understood in contrast to the directional bonding of covalent bonds. The energy of a metallic bond is thus mostly a function of the amount of electrons which surround the metallic atom, as exemplified by the embedded atom model. This typically results in metals assuming relatively simple, close-packed crystal structures, such as FCC, BCC, and HCP. Given high enough cooling rates and appropriate alloy composition, metallic bonding can occur even in glasses with an amorphous structure. Much biochemistry is mediated by the weak interaction of metal ions and biomolecules. Such interactions and their associated conformational change has been measured using dual polarization interferometry, solubility and compound formation. Metals are insoluble in water or organic solvents unless they undergo a reaction with them. Typically, this is an oxidation reaction that robs the metal atoms of their itinerant electrons, destroying the metallic bonding. However, metals are often readily soluble in each other while retaining the metallic character of their bonding. Gold, for example, dissolves easily in mercury, even at room temperature. Even in solid metals, the solubility can be extensive. If the structures of the two metals are the same, there can even be complete solid solubility, as in the case of electrum, the alloys of silver and gold. At times, however, two metals will form alloys with different structures than either of the two parents. One could call these materials metal compounds, but, because materials with metallic bonding are typically not molecular, Dalton's law of integral proportions is not valid and often a range of stoichiometric ratios can be achieved. It is better to abandon such concepts as pure substance, or solute, as such cases and speak of phases instead. The study of such phases has traditionally been more the domain of metallurgy than of chemistry, although the two fields overlap considerably. Localization and clustering. From bonding to bonds. The metallic bonding in complicated compounds does not necessarily involve all constituent elements equally. It is quite possible to have an element or more that do not partake at all. One could picture the conduction electrons flowing around them like a river around an island or a big rock. It is possible to observe which elements do partake, e.g., by looking at the core levels in an X-ray photoelectron spectroscopy spectrum. If an element partakes, its peaks tend to be skewed. Some intermetallic materials, e.g., do exhibit metal clusters, are reminiscent of molecules, and these compounds are more a topic of chemistry than of metallurgy. The formation of the clusters could be seen as a way to condense out the electron-deficient bonding into bonds of a more localized nature. Hydrogen is an extreme example of this form of condensation. At high pressures it is a metal. The core of the planet Jupiter could be said to be held together by a combination of metallic bonding and high pressure induced by gravity. At lower pressures, however, the bonding becomes entirely localized into a regular covalent bond. The localization is so complete that the H2 gas results. A similar argument holds for an element like boron. Though it is electron deficient compared to carbon, it does not form a metal. Instead, it has a number of complicated structures in which icosahedral B12 clusters dominate. Charge density waves are a related phenomenon, as these phenomena involve the movement of the atoms towards or away from each other. They can be interpreted as the coupling between the electronic and the vibrational states of the material. A different such electron-phonon interaction is thought to cause a very different result at low temperatures, that of superconductivity. Rather than blocking the mobility of the charge carriers by forming electron pairs in localized bonds, Cooper pairs are formed that no longer experience any resistance to their mobility.